To calculate the cable resistance, we use the formula resistance equals resistivity times length divided by area. Firstly, determine the area of the cable. Given a 2.5 mm square cable, the area equals 2.5 mm squared, resulting in 6.25 mm squared. Secondly, note the length of the cable, which is 20 meters. Thirdly, the resistivity of copper is given as 17 times 10 to the power of -6 ohms meters. Now apply the resistance formula R equals resistivity times length divided by area. Substituting the given values, R equals 17 times 10 to the power of -6 ohms meters times 20 meters divided by 6.25 mm squared. Ensure consistent units by converting mm squared to meters squared. 6.25 mm squared is equal to 6.25 times 10 to the power of -6 meters squared. Thus, R equals 17 times 10 to the power of -6 ohms meters times 20 meters divided by 6.25 times 10 to the power of -6 meters squared. Calculating this expression yields a resistance of 0.272 ohms. Therefore, the resistance of the cable is 0.272 ohms. To calculate the total resistance of the whole circuit, consider the arrangement of the heating elements. There are 3 elements, each with a resistance of 57.6 ohms. 2 elements are arranged in series, and the third is in parallel with these 2. Firstly, calculate the resistance of the 2 elements in series. When resistors are in series, their resistances add up. Thus, the resistance of the series combination, R series, equals 2 times 57.6 ohms, which equals 115.2 ohms. Secondly, the third element, with a resistance of 57.6 ohms, is in parallel with the series combination. To find the total resistance of the parallel combination, use the formula 1 over R total equals 1 over R series plus 1 over R parallel. Here, R series is 115.2 ohms and R parallel is 57.6 ohms. Substituting these values, 1 over R total equals 1 over 115.2 ohms plus 1 over 57.6 ohms. To solve for R total, first find the reciprocal of each term and then add them. 1 over 115.2 equals approximately 0.868 and 1 over 57.6 equals approximately 0.1736. Adding these values gives approximately 0.2604. Thus, 1 over R total equals 0.2604. To find R total, take the reciprocal of 0.2604. R total equals 1 divided by 0.2604, which equals approximately 38.4 ohms. Therefore, the total resistance of the whole circuit is approximately 38.4 ohms. In summary, the resistance of the cable is 0.272 ohms, and the total resistance of the whole circuit is approximately 38.4 ohms. Let's break down the concepts of resistance and how they apply in series and parallel circuits. Resistance is the opposition to the flow of electric current in a circuit. It is measured in ohms, symbolized by the Greek letter omega. The resistance of a conductor depends on several factors, including the material of the conductor, its length, cross-sectional area, and temperature. The formula for resistance, R equals ρ times L divided by A, quantifies this relationship where R is the resistance, ρ is the resistivity of the material, L is the length of the conductor, and A is the cross-sectional area. Resistivity is a property of the material that indicates how strongly it opposes the flow of electric current. Materials with high resistivity are poor conductors, while materials with low resistivity are good conductors. Copper, commonly used in electrical wiring, has a low resistivity, making it an excellent conductor. When calculating the resistance of a cable, it is crucial to use consistent units. If the length is in meters and the area is in square millimeters, you must convert the area to square meters before applying the formula. This ensures that the resulting resistance is in ohms. In a series circuit, components are connected end-to-end, forming a single path for the current to flow. The total resistance in a series circuit is the sum of the individual resistances. This is because the current must pass through each resistor sequentially, encountering the opposition of each one. Therefore, adding resistors in series increases the total resistance of the circuit and reduces the current flow for a given voltage. In a parallel circuit, components are connected side by side, providing multiple paths for the current to flow. The total resistance in a parallel circuit is less than the smallest individual resistance. This is because the current can divide among the different paths, effectively reducing the overall opposition to current flow. The formula for calculating the total resistance of resistors in parallel is 1 over R total equals 1 over ρ plus 1 over R2 plus 1 over R3 and so on, where ρ, R2, R3 represent the individual resistances. When calculating the total resistance of a circuit containing both series and parallel combinations, you must first simplify the circuit by calculating the equivalent resistance of each combination separately. For series combinations, add the resistances directly. For parallel combinations, use the reciprocal formula. Once you have simplified the circuit, you can then calculate the total resistance of the entire circuit. In the given problem, we first calculated the resistance of the cable using the formula R equals ρ times L divided by A. We then calculated the total resistance of the circuit by considering the arrangement of the heating elements, 2 in series and 1 in parallel. By applying the appropriate formulas for series and parallel combinations, we were able to determine the total resistance of the circuit. Understanding these principles and formulas is essential for analyzing and designing electrical circuits. It allows you to predict the behavior of circuits, calculate currents and voltages, and ensure the safe and efficient operation of electrical systems. Additionally, understanding these concepts allows for proper wire sizing and electrical load calculations, which are crucial in electrical engineering and installations. These calculations ensure that the wiring can handle the current without overheating, preventing potential fire hazards and equipment damage. Moreover, knowing how to calculate total resistance in complex circuits enables efficient troubleshooting and problem-solving in electrical systems. By understanding the behavior of series and parallel circuits, technicians can quickly identify faults and restore the system to proper working order. The concept of resistivity and its influence on conductor resistance is vital for material selection in electrical applications. Copper is widely used due to its low resistivity and high conductivity. However, other materials like aluminum and silver may be used in specific applications where cost or weight considerations are significant. For example, aluminum is lighter than copper and is often used in overhead power lines despite having a higher resistivity. Furthermore, the temperature coefficient of resistance affects the resistance of conductors as temperature changes. Most metals exhibit a positive temperature coefficient, meaning their resistance increases with increasing temperature. This effect is important in high-power applications where significant temperature changes can occur, affecting the circuit's performance. Engineers must consider the temperature coefficient when designing and selecting components to ensure stable and reliable operation across a wide range of temperatures. The principles of series and parallel resistance are fundamental not only in basic circuit analysis but also in more advanced topics like network analysis, filter design, and power distribution systems. Understanding how components behave in these configurations is essential for engineers and technicians working in these areas. Moreover, the concepts extend beyond simple resistive circuits and apply to more complex elements like inductors and capacitors. In alternating current AC circuits, the concept of impedance, which includes resistance, inductive reactance, and capacitive reactance, becomes crucial. Impedance behaves similarly to resistance in DC circuits but also accounts for the frequency-dependent effects of inductors and capacitors. Therefore, a solid understanding of resistance is a foundation for mastering more advanced topics in electrical engineering and electronics. To further elaborate on the calculation of cable resistance, it is important to consider the impact of cable construction and material purity. Real-world cables may have variations in their cross-sectional area and material composition, which can affect their resistance. For example, stranded cables, commonly used for flexibility, have a slightly larger effective area than solid conductors due to the air gaps between the strands. This can lead to a slightly higher resistance than calculated using the nominal area. Additionally, impurities in the copper can increase its resistivity, affecting the overall cable resistance. Manufacturers typically specify the maximum allowable resistivity for their cables to ensure they meet performance requirements. When performing precise resistance measurements, it is important to use calibrated instruments and account for the effects of temperature and contact resistance. Instruments like digital multimeters or specialized ohmmeters are used to measure resistance. However, these instruments may have limitations in accuracy, especially for very low or very high resistances. Contact resistance, which is the resistance at the point of connection between the measuring instrument and the conductor, can also affect the measurement. Techniques like 4-point probing can minimize the impact of contact resistance on accurate resistance measurement. This method involves using separate current and voltage leads to eliminate the voltage drop caused by the contact resistance. In the context of electrical safety, understanding cable resistance is crucial for determining the ampacity or current carrying capacity of conductors. The National Electrical Code (NEC) provides guidelines and tables for determining the ampacity of various types of conductors based on their size, insulation type, and installation conditions. Cable resistance directly affects the amount of heat generated in the conductor due to the flow of current. Excessive heat can damage the insulation and pose a fire hazard. Therefore, it is essential to select cables with adequate ampacity for the intended application to ensure safe and reliable operation. Furthermore, voltage drop calculations are essential for ensuring that electrical equipment receives adequate voltage under load conditions. Voltage drop is the reduction in voltage along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The formula for voltage drop, V equals I times R, where V is the voltage drop, I is the current, and R is the resistance, is used to calculate the voltage drop in a conductor. By knowing the cable resistance and the current flowing through it, engineers can determine the voltage drop and take steps to minimize it, such as increasing the conductor size or reducing the length of the run. In summary, calculating cable resistance is a fundamental skill in electrical engineering and is essential for various applications, including circuit analysis, conductor selection, ampacity determination, and voltage drop calculations. By understanding the factors that affect cable resistance and using appropriate measurement techniques, engineers can ensure the safe and efficient operation of electrical systems. The concepts of series and parallel circuits extend beyond simple resistive networks and are applied in more complex systems involving inductors and capacitors. In AC circuits, inductors and capacitors introduce impedance, which is the AC equivalent of resistance. Impedance includes both resistance and reactance, where reactance is the opposition to current flow due to inductance or capacitance. The impedance of an inductor increases with frequency, while the impedance of a capacitor decreases with frequency. When inductors and capacitors are connected in series or parallel, their impedances combine according to the same rules as resistances. The total impedance of inductors in series is the sum of their individual impedances, while the total impedance of capacitors in series is the reciprocal of the sum of the reciprocals of their individual impedances. Similarly, the total impedance of inductors in parallel is the reciprocal of the sum of the reciprocals of their individual impedances, while the total impedance of capacitors in parallel is the sum of their individual impedances. The combination of resistors, inductors, and capacitors in AC circuits leads to various phenomena such as resonance, filtering, and phase shifts. Resonance occurs when the inductive reactance and capacitive reactance cancel each other out, resulting in a minimum impedance at a specific frequency. Filters are circuits designed to selectively pass or block certain frequencies based on the frequency-dependent behavior of inductors and capacitors. Phase shifts occur when the voltage and current are not in phase due to the presence of inductors and capacitors. Understanding these concepts is essential for designing and analyzing AC circuits used in various applications such as power supplies, audio amplifiers, and communication systems. Moreover, the principles of series and parallel circuits are applied in digital electronics as well. In digital circuits, transistors are used as switches to control the flow of current. These transistors can be arranged in series or parallel to implement logic gates such as AND, OR, and NOT gates. The behavior of these logic gates is determined by the arrangement of the transistors and the voltages applied to their inputs. By combining these logic gates, complex digital circuits can be designed to perform various functions such as data processing, memory storage, and control systems. The concepts of series and parallel resistance are also relevant in sensor design and instrumentation. Many sensors rely on changes in resistance to detect physical quantities such as temperature, pressure, or strain. These changes in resistance can be measured using Wheatstone bridges, which are circuits consisting of 4 resistors arranged in a diamond configuration. When the resistance of one of the resistors changes, the bridge becomes unbalanced, producing an output voltage proportional to the change in resistance. By carefully selecting the values of the resistors in the bridge, the sensitivity and linearity of the sensor can be optimized. In summary, the principles of series and parallel circuits are fundamental concepts that are applied in various fields, including electrical engineering, electronics, digital logic, and sensor design. Understanding these concepts is essential for analyzing, designing, and troubleshooting electrical and electronic systems. From basic circuit analysis to advanced applications in AC circuits, digital systems, and sensor technology, the principles of series and parallel circuits provide a foundation for solving complex problems and creating innovative solutions.